Work, energy, and power. In introduction, the terms work, energy, and power are frequently used in everyday language. A farmer plowing the field, a construction worker carrying bricks, a student giving an examination, or an artist painting a beautiful landscape. All are said to be working. In physics, however, work covers a definite and precise meaning. Somebody who has the capacity to work for 14 to 16 hours a day is said to have a larger stamina or energy. We admire a long distance runner for her stamina or her energy. Energy is thus our capacity to do work. In physics, too, the energy is related to work in the sense, but as said in the above term, it is used in everyday life with different shades of meaning. These are delivered at a great speed. This shade of meaning is close to the meaning of word power in physics. We used to find that there is at best a loose correlation between the physical definitions and physiological pictures or terms that generate in our mind. The aim of this chapter is therefore to develop an understanding of these three physical quantities. The, scala, the scalar product. We've learned about vectors and their use in chapter 4. Physical quantities like displacement, velocity, acceleration are vectors, and we have also learned how vectors are needed or applied, added or subtracted. We now need to know how vectors are multiplied, and these are two ways of multiplying vectors which we shall come across. One way, known as a scalar product, gives a scalar from two vectors, and the other is that a vector product produces a vector. Here we can take up scalar product of two vectors. The scalar product of dot product of any two vectors a and b is denoted as a dot b. A dot b is equal to ab cos theta, where theta is the angle between the two vectors as shown. Since ab cos theta are scalars, the dot product of ab is a scalar quantity. Each vector a and b has a direction, but their scalar product does not have a direction. A dot b is equal to ab cos theta. Ba cos theta is equal to ba cos theta. Geometrically, b cos theta is the projection of b into a, and a cos theta is a projection of a into b. AB is a product of the magnitude of a and the component of b alongside a. A dot b is equal to b dot a dot b plus c is equal to a dot b plus b dot c. I cap into I cap plus j cap into j cap plus k cap into k cap is equal to 1. I cap plus j cap is equal to j cap plus j cap dot k cap is equal to k cap dot I cap is equal to 0. A is equal to ax I cap plus by j cap plus az k cap. B is equal to bx I cap plus by j cap plus bz k cap. A dot b is equal to ax I cap plus ay j cap plus az k cap. Bx I cap by j cap plus bz k cap. A dot a is equal to mod of a into a cos theta. Notions of work and kinetic energy. Work energy theorem. The following relations for rectilinear motion under constant acceleration has been encountered in this chapter, where u and v are the initial and the final speeds and s is the distance traversed. Multiplying both sides by m2, we have 1/2 mv square minus 1/2 mu square. V square minus u square is equal to 2ad. Work done by a force on the body over a certain displacement. Change in kinetic energy of a particle is equal to work done on it by a net force. We shall generalize the above derivation by varying force in later example. Work. As earlier seen, work is related to the force and displacement over which it acts. Consider a constant force of F acting on a particle of mass m, and the object undergoes a displacement in the positive direction of x. The work done by the force is defined as a product of component of force and the direction of displacement. W is equal to F cos theta is equal to F dot D. In to see that there is no displacement, there is no work done, even if there is force, even if the force is large. No work is done if the displacement is zero, as seen in the example. A weightlifter holding 150 kg steadily on his shoulder for 30 seconds does no work on the load during the time. The force is zero. A block of moving or smooth horizontal table is not acted upon by a horizontal force. The force and the displacement are mutually perpendicular, and this is so since theta is equal to pi by 2, 90 degrees cos theta is equal to 0. And for the block moving a smooth horizontal table, the horizontal force mg does no work since it is moving at right angles. Work can be positive and negative if theta between is the angle between 90 degrees to 0 degrees, it is positive, and that between theta between 90 to 180 degrees is negative, because cos theta is negative. The work done by friction is negative, so cos 180 is minus 1. The SI unit of energy is joule, and since work and energy are so widely used as physical concepts, alternative units abound, and some of these are listed below. Work done at a variable force. A constant force is rare, and the variable force with which it is moving is commonly encountered. If displacement delta x is small, we can take the force f of x as approximate constant. Work done is then W is equal to f delta x work energy theorem for a variable. We are now familiar with the concepts of energy and kinetic energy. To prove that work energy theorem for a variable force is d by dt of 1/2 mv square. Thus, work energy theorem is proved as a variable of force. While work energy theorem is useful in a variety of problems, it does not in general incorporate the physical complete dynamic information of Newton's second law. It is an integral form of Newton's second law, and Newton's second law is a relation between acceleration and force at an instance of time. Work energy theorem involves an integral over time interval, and in this sense the temporal time information contained in this statement. The concept of potential energy, the word potential suggests possibility or capacity for action, and the term potential energy brings to one's mind stored energy. A stretched bowstring possesses potential energy when it is released, and the arrow flies off at a great speed, the Earth's crust is not uniform, but as it continues or dislocates, that is called fault lines, and these fault lines on the Earth's crust are called compressed springs. They possess a large amount of potential energy. Mm, an earthquake results when fault lines readjust. Thus, potential energy is stored energy by virtue of position or configuration of a body. The body left to itself releases the stored energy. Let us make a notion of potential energy. The gravitational force of a ball or a mass m is mg, and g may be treated as a constant near the Earth's surface. By near, we imply that the height h is compared to the Earth's radius, so that we can ignore the variation of g near the Earth's surface. In This equation can be written as 1/2 mv square is equal to mgh, which shows that at gravitational potential, the energy of a body at height h, when the object is released, manifests itself as kinetic energy, and that of an object reaching the ground manifests itself as potential energy. Physically, the notion of potential energy is applicable only to classes of forces where work is done against the force gets stored up as energy. When external constraints are removed, it manifests itself as kinetic energy. Mathematically, f of x is equal to minus dv by dx. The work done by a conservative force such as gravity depends on the initial positions. The work done by a conservative force such as gravity depends on the initial and the final positions. So if an object of mass m is released from rest from the top of a smooth frictionless inclined plane of height h, it is simple. It is at the bottom, that is under root 2 gh. The dimension of potential energies are m raised to 1, l raised to 2, and e raised to minus 1, and the unit joule for energy. The conservation of mechanical energy. For simplicity, we demonstrate this principle for one-dimensional motion. Suppose that a one-dimensional body undergoes displacement delta x under the action of conservative force. Delta k is equal to f of x delta x, which means that k plus v is the sum of the kinetic and the potential energies of a body. Let us consider some of the definitions of conservative force. A force f of x is conservative if it can be derived from a scalar quantity Vx by the relation. The three-dimensional generalization requires the use of a vector derivative which is outside the scope of the book. The work done by a conservative force depends on the endpoints. This can be seen from the relation. W is equal to k of j minus k of t. V of x 1 minus v of x v of x v of x of f. A third definition shows that work done by this force is in a closed path 0. This once again is apparent since x of I is equal to x of f. Total mechanical energy of a system is conservative if the forces done during work are conservative. Potential energy of a spring. The spring force is an example of a variable conservative energy. The other end of the spring is attached to a rigid wall. The spring is light and may tend to be as massless. If an ideal spring of spring force Fs is proportional to x, where x is the displacement of the block from the equilibrium position, the displacement could be either positive or negative. The force of law of the spring is called Hooke's law, and the constant is called spring constant. The expression may be obtained by considering the area of the triangle as in figure 6.7, and note that the work done by the external pulling force F is positive since it overcomes the spring force. So the work done by the spring in cyclic process is zero. We have explicitly demonstrated that spring force is position dependent and only as first stated by Hooke. F of s is equal to minus kx final positions. Thus the spring force is conservative. Mm, we conclude from this section by making a few remarks on conservative forces. The information on time is absent for the above discussions. In the example considered above, we calculate the compression but not the time over the compression. A solution of Newton's second law for this system is required for temporal information. Not all forces are conservative. Friction, for example, is a non-conservative force, and the conservation or the principle of energy will be modified in this case, and the zero of potential energy is arbitrary, and it is said it is a set of non-according or non setting non-convenience for the constant gravitational force mg. We look at v0 on the earth's surface. In the later chapter we shall see that of a force due to universal law of gravitation, 0 is best defined at an infinite distance from the gravitational source. Various forms of energy, the law of conservation of energy. In the previous section, we have classified into two distinct categories, one based on motion, namely kinetic energy, and the other on configuration or position, namely positional energy. Energy comes in many forms which transform into one another in ways which are not often clear to us. Heat. We have seen that frictional force is not conservative. However, work is associated from force of friction. A block of mass sliding down a rough horizontal surface with speed v naught comes to a halt over a distance x naught, and the work done is the force of kinetic energy. If we continue our scope to mechanics, we would say that kinetic energy of the block is lost due to the frictional force. On examination of the block and the table, we detect a slight increase in their temperatures, and the work done by the force is not lost, but it is transferred as heat energy. This raises the internal energy of the body and the table. In winter, in order to feel warm, we generate heat by vigorously rubbing our palms together. We shall see later that the internal energy associated with these ceaseless, often random motions of molecules, a quantitative idea of the transfer of heat energy, is obtained by nothing that 1 kg of water releases about 42,000 joules of energy. One of the greatest technical achievements of humankind occurred when we discovered how to ignite controlled fire. We learned to rub two flint stones together, mechanical energy, and got them up to ignite a heap of dry leaves, chemical energy, which then proved sustained warmth. A matchstick ignites into a bright flame when struck against a specially prepared chemical surface. The lighted matchstick, which applies a firecracker, results in a spectacular display of sound and light. Chemical energy arises from the fact that molecules participating in the chemical reaction have different binding energies. A stable chemical compound has less energy than the separated parts. A chemical reaction is basically an arrangement of atoms if the total energy of the reactants is more than the total energy of the products. It is said to be exothermic if it gives out heat, and the reaction is said to be endothermic if it absorbs heat. Chemical energy is associated with forces that give rise to stability of substances, and these forces bind atoms into molecules. Chemical energy arising from combustion of coal, cooking gas, wood, and petroleum is indispensable to our daily existence. Electrical energy. The flow of electrical energy causes bulbs or fans to glow or rotate or bells to ring. When they are laws governing the attraction and repulsion of charges and currents, which we shall learn later. Energy is associated with an electric current. An urban Indian household consumes 2200 joules of energy, and the equivalence of mass and energy. Till the end of the 19th century, physics believed that in every physical and chemical process, the mass of an isolated system is conserved. Matter might change its phase, that is, glacial ice could melt into gushing stream, but matter is neither created nor destroyed. This is what Albert Einstein proved. Nuclear energy, the most destructive weapon made by man, the fission and fusion of bombs and manifestation of the above equivalence of mass and energy. On the other hand, the explanation of life nourishing energy output of the sun is also based on this equation. In this case, effectively, four light hydrogen nuclei fuse to form a helium atom. In fission, a heavy nucleus like uranium is split by a neutron into a lighter nucleus. Once again, the final mass is less than the initial mass, which can be tapped to provide an electrical energy, as in nuclear power plants. Strictly, the energy delta E released in a chemical reaction can be related to mass defect. Delta M is equal to delta E by C square. However, for a physical reaction, the mass effect is much smaller than that for a nuclear reaction. We point out a common misconception created by newspapers and magazines, that they mention that food values in calories urge to restrict diet intake below 240 calories. What they should say is in kilocalories and not in calories. A person consuming 240 calories in a day will starve to death. One food calorie is 1 kilocal. The principal conservation of energy, we have seen that the total mechanical energy of a system is conserved if the forces are doing work. If some of the forces involved are non-conservative, part of the mechanical energy may get transformed into other forms, such as heat, light, and sound. The principle of conservation of energy cannot be proved. However, no violence to this principle has been observed. The concept of conservation of or transformation of energy is in various forms linked together, various branches of physics. From engineering point of view, all electronic communication and mechanical devices rely on forms of energy. Power. Often it is interesting to know that work done on an object but also relates to the rate at which an object for which work is done. We say that a person is physically fit if he not only climbs 4 floors of a building but climbs them fast. Power is defined as the rate at which you do work. Summary. Work energy theorem states that the change in the kinetic energy of a body is work done by the net force of the body. A force conservative if work done by it is on an object is zero, independent of the path on which it is done. For a conservative force in one dimension, we define a potential energy function. The principle of conservation of energy states that the total mechanical energy of a body remains constant if the only forces that act on the body are conservative. The elastic or potential energy of a spring or an extension v of x is equal to 1 half kx square. Scalar or dot product a dot b is written as a or b. A I cap dot I cap is equal to j cap dot j cap is equal to k cap dot k cap. I cap dot j cap is equal to j cap dot k cap is equal to k cap dot I cap.